Okay, let's let me welcome all of you to the second lecture of this course, that is High-K dielectric material for the CMOS technology. In the previous class, we studied how the MOS capacitor behaves and what are the topics over there, like the different operation region and different non-idealities, get doping, and this lecture is the follow-up from there, that is the MOSFET, that is metal oxide semiconductor field effect transistors. And this is the one of the most important lecture in our course, which will set the basics or set the tone of our entire class from now on. So as I spoke before, today we are going to dive into the fundamental building block of the modern electronics, and that is MOSFET, or metal oxide semiconductor field effect transistors. That's the full form of it. So as you can see in this diagram, we have a structure with source, gate and drain. So imagine, you can imagine that the source and drain are the entry and exit points of the electron or any charge particles, depending on the polarity or of this whole or the type of carrier of this device. Let's keep in this abstract level the type of carriers. Let's not go much details, but still we know that for p body semiconductor with n plus region buried here, we are talking about n-type MOSFET, where electrons are the one who is conducting the current, and electron is a minority carrier in this p body. So who is supplying the electrons? These n plus regions. And when they are getting supplied, when the channel is inverted, we create something like a wire or connection between these two heavily doped n plus regions. Now what creates this region? That is the main phenomenon which has driven the name. So FET means field effect transistor. And what has kind of driven the reason behind this name? That when we apply some voltage over the gate, and that creates an electric field which controls the channel regions or the surface carrier polarity, as we have seen in the capacitor lesson, and this n plus region will then supply the electrons or the to maintain the flow of the current. So as we can see here, for 1.8 volt we have higher current when the VG is 1.8 volt, but when VG is 0 we don't have much current. So that's why the name comes here. So basically we can think transistor as a water faucet. The gate is the handle which controls the water flow or the flow of the water between source and drain. Now MOSFETs are quite essential because they can be scaled, efficient, and they are fast. So that's why they are the heart of everything, from smartphone to computers, everything almost. So the key takeaway is that the gate voltage modulates this channel conductivity, and that allows to switch the MOSFET between the off and on state. And this switching behavior is very much essential for the digital logic applications. Ideally, one MOSFET should have high input resistance but low output resistance, and they should have the ability to amplify the signals. So this makes the MOSFETs versatile for various analog and digital circuits. Now in reality, the device physics is far more complex than what I am telling right now. It has channel length modulation, velocity saturation, quantum effects, and those become significant at nanoscale dimensions. So the graph shows the IV characteristics, but it doesn't really capture the nuance of the short channel effects like the Dibble or Giddle. The Dibble stands for drain-induced barrier lowering, and Giddle stands for gate-induced drain leakage. So those impact the device performance and power consumption. On top of that, the choice of material, doping profile, and oxide thickness, everything significantly influence the MOSFET's threshold voltage, subthreshold swing, and also the transconductance. And also you can see that in present days our designs are much beyond this planar MOSFET. We have moved to FinFET, gate-all-around FET, and then metal oxide based TFT, 2D material transistor, and this is what we are aiming even today to scale down. And there the oxide thickness and the quality of the oxide plays an important role. So as I told that this chapter will be laying the basics of this our whole course, so please pay attention to the following lecture slides. Alright then, so now what we have some basic understanding of the MOSFET, and the MOSFET's most common and most popular use is the CMOS technology. So before CMOS there was a life only with N type of MOSFET, and as the development evolved and we came up with the both P and N type of MOSFET, and I can say that it's not that easy to develop both of them together, and there are a lot of physics, lot of engineering, and lot of trial and errors are involved. So I can tell one thing: when you do the process, let's say well, all of you are in currently Taiwan, so if you are doing the process in NTHU and now you go to NYCU to do the process, you have to change the process parameters. So if you think that okay, we have N-type MOSFET, what's the big deal in bringing up the P-type? No, it's not easy. You have to tune every parameters very precisely, from the electrodes to doping profile, also the doping concentration and type, and also you have to ensure that how and when you will dope, like whether you want to dope the P-type first or N-type first, and how you want to isolate the N-type region while doing the P-type. You have to think everything together, so it's not that easy. It's very tedious and time consuming. So I always there was a time, so I was a digital engineer, like I used to write codes on FPGA. So when I started doing the process, or better to say when I started learning the semiconductor devices, I was not much appreciative about the efforts. So I was doing SPICE coding and TCAD for a year, almost for a year, first year of my PhD, and then fortunately I got the chance to work on the FinFET development, and then I understood how difficult, how critical each parameters are. So if you want to do bulk, you have to do almost more than 100, like 130 or 150 steps. If you're doing SOI, then it can be reduced to 60 steps. So you can see a little difference from SOI to bulk, how many differences you have to do, how many more number of steps you have to do. So you always have to be appreciative of those people who are spending their time in the clean room and developing this process. So for them, now we have the CMOS technology, where the gate oxide thickness is very small. Even we can think of in the Armstrong level at this moment, and we will go much details how we are dealing with that and how we are dealing with the gate oxide thickness scaling, whether the tunneling or whether their insulating properties are still there or they are losing. So we will go much more details in our next few slides. Now let's look into the details of this CMOS technology. This is the circuit of the CMOS inverter. So this is the fundamental building block of the digital circuit. It is used to invert one signal, turning 0 into 1 and 1 into 0. So if we start with the schematic here, we see the PFET connected in a specific way with the VDD on the source and two drains of the NFET. The drain of the PFET is connected to the drain of the NFET, and the source is at 0 volt, and two gates are connected together and two drains are connected together, and the and the input is applied to the gate of the both of the transistors, and the output is taken from the common connection at the drain between PFET and NFET. So we can think it like a seesaw. When the input is low, the PFET turns on, so it pulls the output high, and the capacitor is charged, and this also happens, the vice versa happens. When this is low, the input is low, so what happens, that PFET turns on, and when the input is high, the NFET turns on. So this will discharge, the capacitor will discharge through here, and then we see low voltage here. So when V in is 0, so the PFET is on, so the gate to source voltage is minus VDD, and the NFET is off because the gate to source voltage is 0 volt. So this pulls the V out up to VDD to the supply voltage. So conversely, when the V in is VDD, PFET turns off because of the gate to source voltage is 0, and the NFET is on because the difference is VDD, and this pulls down the V out to 0. So the capacitor here, this represents the load capacitance, which includes the capacitance of the interconnect and the input capacitance of the next stage. So this affects the switching speed of the inverter. Now if you see on the right hand side, it shows the layout. You can see that the N well is in the P substrate. So we have to create an N well inside the P substrate where the PFET is located. This is necessary because PFET requires an N-type region, and we also need to have these contacts. So they represent the connection to the metal layers, and the metal layers are used to route signals and powers. And then the layout is designed to minimize the area and optimize the performance. In advanced CMOS technologies, this layout becomes increasingly complex, with multiple metal layers and sophisticated design rules to ensure proper operation and minimize the parasitic effects. So now if we bring all of them together, so CMOS inverter is a crucial component in digital circuits. It is used to implement logic gates and other digital functions. Its operation relies on the complementary nature of the NFET and PFET, and we have to also design this layout carefully in order to optimize the performance, minimize the area. Well, now we want to focus on a very critical factor that determines the speed and performance of the MOSFET. So what is that? The mobility. So we are specifically looking at the surface mobility, which is the ease with which the electrons and the holes move within the inversion layer of the MOSFET. So let's start with the key points. We want MOSFETs to switch quickly. This means they need to charge and discharge circuit capacitances first. To do that, we need large transistor current. So we can think of it like water flowing through a pipe. A wider pipe allows to flow faster, and a narrow and the bad pipe doesn't. So this this means that the electrons and hole mobility in the surface layer or the surface inversion layer are of our concern at this moment. So how easily the charge carriers move in the channel of the MOSFET is determined by the surface mobility. So higher the mobility, it means faster movement, so which translates to higher current and faster switching. Now let's get a bit more technical. So the diagram here that shows the cross section of the MOSFET with some relevant parameters like oxide thickness and the depletion layer width, and also the inversion layer, and also the drain current that is flowing through here. And so basically, so what is important for us? The important is the mobility, that is hole and electron mobility at the surface. So how come? Because the equation of the n-type MOSFET is given by this. And the graph on the left side shows the relationship between the carrier mobility and gate voltage for both n-type and p-type. And we can also see that how the mobility changes with the gate voltage. So now the equation for the mu ns and mu nps are provided, and we are not going into the detailed derivation of this. This is not the device physics course, that's why I'm leaving it behind. But you can see that the mobility takes into account what are which parameters. So the VGS, and also the oxide thickness, and also the threshold voltage. So if we consider the complexities of the surface mobility, we will find that surface scattering, Coulomb scattering, phonon scattering are some factors that affects the mobility in the inversion layer. So these equations are empirical models, and they may not fully capture the complex physics of this carrier transport, especially in advanced MOSFETs with the novel materials and structures. And this graph here shows the experimental data, model predictions, and that also highlights the challenges of accurately modeling the carrier mobility. So nowadays we are constantly exploring all the new materials and device architecture, and that also adds different levels of complexity in this equation. So what we can say that surface mobility is a very crucial parameter. It determines the speed and the performance of the MOSFET, and if we have higher mobility, it leads to higher current, faster switching. And therefore, even if you do not understand, or even if you cannot accurately get a proper equation of these mobility factors, but it is very important to understand the factors that affect the mobility. Why? Because we want to control those parameters for designing high performance devices. Well, let's imagine that we have a tiny electron, and that's trying to zip through the heart of the computer chip. So the electron is not just moving through any material, it's moving on the silicon surface, and how fast the electron goes, that depends on the how is that surface is arranged. It's a bit like trying to run on a perfectly smooth track versus a bumpy one. So today, as we are talking about the surface mobility, the ease with which the electrons and holes move along this silicon surface, and what we have discovered is that the orientation of the surface and the direction of the movement of the electron makes a huge difference. So silicon is the material our chip is made of. It's crystal. So just like the brick wall has a pattern, so silicon atoms are also arranged in a specific way. So we can cut the crystal in different directions, creating different surfaces. In standard CMOS technology, we use what's called a 100 surface. It's like choosing the smoothest track for our electrons, and we just do not care about the surface, we also care about the directions our electrons and holes are moving. So in our chips we design transistor so that both electrons and holes flow in the same direction, what we call the 0-1-1 direction. It's like making sure that everyone is in the same lane. And now, why did we choose this particular surface and direction? Well, it turns out that this configuration gives us the highest electron mobility. The electrons you see at the speed, they are the one that is the speed demons of the chip. So they move much faster than the holes. So by choosing 100 surface, we are giving our electrons best possible track. But here's the twist. This is not the best surface for the holes. The hole is slower than the electrons, don't get as much of boost. It is like giving a sprinter the best shoes, but the marathon runner gets the average one. So why does it happen? Well, it comes down to the fundamental physics of the silicon, that the orientation effects can be explained using something like Schrodinger's wave equation, and this equation helps us understand how the electron behave in a crystal lattice. It tells us that the energy levels of the electron and holes are affected by the surface orientation, which in turn affects their mobility. And there's more. The way surface is oriented and the direction of the current flows also affect how the mobility respond to the mechanical stress. So you can imagine it as the pushing or pulling on silicon. It changes track and the electrons and hole moves differently, and this is crucial for understanding how our chips perform under different conditions. So if we summarize, we choose 100 surface because it gives us the best electron mobility. Even if it is not perfect for holes, it is a compromise, a balance like many things in engineering. And as always, we have to come up with some kind of trade-off in every design. Let's resume to audio only because the video is unnecessarily taking the space of the drive, and we have some limited space while uploading. So in this slide, now we are going to learn the threshold voltage and how it is affected by something called the body effect. So remember that the threshold voltage is the minimum gate voltage that is required to turn on the MOSFET. It's like the starting point of the current flow. In ideal situation, VT would be a fixed value, but in reality it can change. And one of the factors that affect the body affects is the body effect. So imagine the MOSFET, it's like having two capacitors. One is the oxide capacitance here, and the another is the between the channel and the body, and that is the depletion layer capacitor. So typically the inversion layer in the MOSFET that acts like a thin resistive film that connects the source and drain, and this film at the source potential Vs forms a capacitor with the gate oxide as the dielectric. It also forms a capacitor with the body within the depletion layer, and as the dielectric the depletion layer capacitance is given by C depletion, and now the voltage difference between the body between the source and body, that is VSB, it induces a charge in the inversion layer, and this affects the overall charge required to turn on the MOSFET, and hence that affects the VT. Now let's look at the equations here. So now this is my Q inversion, and when I have the VSB, I mean a non-zero voltage difference between source and body, then I will have another voltage drop associated with it, and this is called the, I mean, now if we want to have the voltage drop across that, now if we want to have the voltage drop across that, then the equation of this Q inversion changes by a factor of Vt plus this ratio of this depletion and oxide capacitance multiplied by the source to body voltage. And now we can see that my Vt is dependent on the source to body voltage. And if we equate that, we will come to a term alpha. And alpha can be simplified to this equation, where 3 comes from the ratio of silicon and SiO2 epsilon values. So that means that if I have a positive difference in the VSB, then I will increase my VT. So what does positive voltage means? That I have some voltage here, that is the, let's say I'll put some positive voltage here, so that will create some difficulty in getting the charges across this inversion layer. So sometimes therefore we also use this body as the backgate that is weakly linked towards this inversion layer. So body can also be used as the backgate in our MOSFET devices, typically bulk. Well, now what the MOSFET does, the modern transistor, they employ something called steep retrograde doping profile, which is light doping here and in a thin surface, and then a very heavy doping underneath. So the steep retrograde doping that allows transistors scaling to smaller sizes and cost reduction, and also reduces the impurity scattering. The depletion layer thickness it's basically the thickness of the lightly doped region. Now as the source to bulk voltage increases, the depletion layer does not change significantly. So therefore the depletion region capacitance are alpha and alpha are basically constant. So as a result, modern transistors exhibit more or less linear relationship between Vt and the source to bulk voltage. A linear relationship means that the maximum depletion region width and the ratio of this of this capacitance in the oxide and the depletion capacitance are independent of the body bias. In earlier generation, the body doping used to be something like uniform doping, which is shown here. In that case, the theory for the body effect is more complicated, where this Vt can be obtained by replacing the phi 2b term with phi 2b plus source to bulk voltage, and therefore this gamma is called the body effect parameter, and Vt is not the linear parameter of in the equation. So sometimes we can do Taylor expansion to linearize this. Now we can understand the impact of this inversion charge. So when we apply a source to drain voltage, so what happens? So we are moving beyond the simplified scenario where VDS is 0. When VDS is non-zero, so you can see here, so we have some voltage drop across here to here, these 2 points, and the voltage drop is not constant in all points, so they are the function of this length. So that is the channel voltage, becomes the function of this position. It varies from Vs to Vd, and this variation means the voltage across the oxide and the depletion layer capacitors decrease as we move towards along the channel towards drain. So this leads to reduction in the inversion layer charge as we move from source to drain. To accurately model this, we have to replace VGS, this term, with a function of VGS, which is function of X, or VGS minus VCS, and then our whole equation for Q inversion becomes like this, which is COX multiplied by VGS minus channel voltage, and then our body effect parameters along with the channel voltage. So now this factor, this modified equation for Q inversion incorporates a factor called M, which is 1 plus alpha, and that accounts for the body effect's influence on the charge on the channel charge distribution. Now we can see that the body or the backgate has similar but a weaker effect on the channel charge as the compared to the gate, and the M typically its value is around 1.2, but we can also use M as 1. So bulk charge effect is something that is intrinsically linked to this body effect, and it further emphasizes the complexity or the complex interplay of voltage and charges within the MOSFET structure. Now let's break down this slide of this basic IV model. So we will see a bit of physics and also the equation that describe the relationship of this drain current with the drain to source voltage. So under non-zero VDS, so previously we explored MOSFET operations under simplified conditions of VDS 0. Now we will see more into the realistic scenario when VDS is non-zero. So this introduces complexities because the channel voltage is no longer uniform but varies along the channel length. To analyze this, we employ the gradual channel approximation, which assumes that electric field along the channel is much smaller than the field perpendicular to the channel. So this allows us to consider the channel as a series of infinitesimally small sections with each slightly different channel voltage. Now as VDS increases, the voltage across the oxide and the depletion layer capacitor decreases along the channel. So this leads to reduction in the inversion layer charge as we move from source to drain. To account for this variation, we modify our previous equation of Q inversion by this VGS minus VCSX, and we also take into account of this body effect. So this gives us that Q inversion will be COX multiplied by VGS subtracted by VCS minus VT0, and it will be also subtracted by alpha multiplied by VSB plus VCS. So if we rearrange that and we come to this equation, so we have the bulk charge factor M here. M accounts for the body effect's influence on the channel charge distribution. It also represents the fact that body has a similar but weaker effect on the channel charge as the gate itself. And then also we have to take into account the effect of W and L, and also the mobility, and which is affected somehow by the electron drift. And this is our complete equation, and at saturation we can say that this is our this is the ID looks like. It can be found by differentiating the ID equation and setting it to 0, that for the voltage at the saturation voltage. So now the MOSFET has two operation region. One is the linear and another is the saturation. In the linear, the transistor behaves like a resistor, and at the saturation, IDS become constant and it's independent of VDS. As VDS equal to VDSat, the inversion layer at the drain end of the channel disappears. It's called the channel pinch-off. Beyond VDSat, a short high field pinch-off region exists where inversion charge is 0. And the voltage is dropped across it. Despite the pinch-off, the current continues to flow, because even if we have the pinch-off, the current continues to flow because the electron reaching the pinch-off region are swept down the steep potential drop. This thing is equal to something like a mountain of stream feeding into a waterfall, and the flow rate in the stream is determined by the slope of the river bed. So the flow rate can be IDS, and the slope of the river bed is the DEC dx, and the amount of water in the stream is equal to inversion charge. So what are the key takeaways? So when VDS is non-zero, the channel voltage varies across the channel length. The variation affects the inversion layer charge and leads to drain current. The bulk charge factor M accounts for body's effects on the influence of the channel charge distribution. The MOSFET operates in two regions. Channel pinch-off occurs as VDS equal to VDSat, but the current continues to flow through pinch-off region. Now this is the channel voltage profile at saturation, and this is also beyond saturation. So what are the key takeaways from here? That the channel voltage profile is parabolic when VDS is equal to VDSat. It indicates a gradual increase in voltage from source to drain. So this equation here, it describes the VCS as a function of X. As you can see that when the VDS equal to VDSat, the equation is derived by substituting the upper limit of some equations, and we are not going into the details. So we will just see what are the key takeaways. So, and also if you see the Q inversion, it shows that current density is constant along the channel, and beyond saturation, a pinch-off region forms near the drain. So therefore, the excess voltage is dropped across that region, and the current density also remain constant along the channel even beyond saturation. This explains why the IDS stays constant in the saturation region.